We are still up here in our energy budget and temperature explanations, and going back to our energy budget. First, I'll say, as we've seen, CO2 and methane and these other greenhouse gases are naturally occurring gases. And so we've had, I just want to make the distinction that the greenhouse effect is not some new thing that humans are causing. We have a natural greenhouse effect on Earth, which is a good thing, and it's caused the Earth to be warm enough to have liquid water and to have life. But what humans are doing is enhancing the greenhouse effect. They're increasing the greenhouse effect on Earth by increasing the concentrations of greenhouse gases. And so we mostly talk about CO2, talk a little bit about methane, and then nitrous oxide is another greenhouse gas that's, I'll show you exactly how important it is for contemporary global warming. But I just wanted to show you that here's a graph of those things. And so on the left side is, so we have carbon dioxide, methane, nitrous oxide. On the left side is the concentrations of those gases in the atmosphere. So we talked about like CO2 in pre-industrial was about 280 parts per million. And this is going back 10,000 years to the present, so time before 2005. So 10,000 years ago, around 280 parts per million, very stable for a long period of time, and then spiked up, of course, when we started burning fossil fuels. And then methane, if you look, that has this other acronym. So instead of parts per million, it's parts per billion. So methane was like at 750 parts per billion for a long period of time, and then that spiked up. And then nitrous oxide was also measured in parts per billion. So like 250 parts per billion, and that spiked up. And so that kind of makes you think about like, well, how do you compare these in terms of their influence on global temperature? Like, is it fair to say that, oh, well, methane, since it's measured in parts per billion and has a way smaller concentration, like that must be way less important than carbon dioxide? Like, probably not, right? Like, we don't necessarily know if there's some other property of methane that would make it more important, even at smaller concentrations, that type of thing. So the answer to that question is kind of answered on the right side of these diagrams. And that's with this term, radiative forcing, which is this term that I'm talking about today. And so radiative forcing allows us to compare the influence of different things on the Earth's energy budget, and thus their influence on temperature. So you see that radiative forcing over here is up to like 2 watts per meter squared for CO2, and it's smaller for methane, and it's smaller still for nitrous oxide. But okay, what does this actually refer to? What is this radiative forcing? It's exactly something that we've already been looking at. It's going back to our first law of thermodynamics. And it's basically just this top part of our first law of thermodynamics, this energy in versus energy out part. So the radiative forcing is the energy imbalance at the top of the atmosphere between energy in and energy out. And you know, one way to think of it is that it's a force that's causing the Earth's radiative energy budget to change. And so then that's gonna be how we change the Earth's temperature, because temperature is a measure of energy, it's a measure of kinetic energy of the molecules of the Earth. So it's called a radiative forcing because we're talking about electromagnetic radiation. So these components are radiation. And then forcing is just this idea that you're pushing the energy budget in one direction or another. You're forcing it to change in one direction or another. And so that's going to be the only way that we can essentially change the Earth's temperature over a long period of time. To get warming or cooling, you have to impose a radiative forcing on the Earth's energy budget. So yeah, to answer the question, radiative forcing allows us to compare it allows us to compare anything to anything. So this is very, very useful. Is why I'm bringing it up. It allows us to compare the influence of changes of very different things on the Earth's energy budget. So it's doing this because it's converting all of those changes into a common currency, which is this watts per meter squared energy imbalance. So it'd be like, it's kind of like if you wanted to compare trade between the United States and China or something, and you say, okay, the United States, buys a bunch of electronics from China, and I don't know what we send to China. Like let's just say it's something totally different. Let's say we send bananas to China or something, which is totally wrong. But if you're to compare electronics to bananas, how would you compare those? Would you say, okay, let's weigh them and compare them in kilograms, or let's look at the volume and compare the volume shipped between the United States and China? Like that wouldn't make any sense. We compare them in a common currency. We compare them in dollars or international dollars or whatever. Like you convert those things into some common currency so you can compare them. And so that's the same idea here, is that you can have changes in the environment which seem like, how do you compare them? Well, if you convert them into this change, like what they do to the Earth's energy imbalance, in terms of watts per meter squared, then you can compare them and you can say whether or not, one has a larger influence on the temperature than another. So like one example would be, you can compare the influence of the sun getting brighter versus the increase in CO2. So both of those things actually have happened since the Industrial Revolution. I'll show you in a second that the sun getting brighter is very small compared to the increase in CO2. Or you can compare these things that I was just mentioning, like the change in CO2 concentrations versus the change in methane concentrations. Even though they're at very, very different concentrations of the total atmosphere, you can compare their influence by converting them into a radiative forcing, into this common currency of watts per square meter. So even kind of a better example, because they seem more uncomparable at first, would be comparing the influence of, for example, converting forests to farmland to the influence of CO2 on both on temperature. So if you were to say, okay, we're increasing CO2 since the Industrial Revolution, we're also changing forests to croplands since the Industrial Revolution, how do we compare those two changes in terms of like which is bigger for the change in temperature? Well, converting CO2 or putting more CO2 into the atmosphere is going to affect the energy budget by inhibiting this outgoing long wave radiation. Converting forests to croplands is going to change the energy budget as well, because it's changing kind of dark forests to lighter croplands. And so you're changing the albedo due to that. So you can look at both of those in terms of their effect on the energy budget and then compare them that way. So of course, this is all temperature focused. This is all focused on the global average temperature and the global average energy budget. And so if you're concerned about something else, like just, the quality of the local land or something, you would have to convert it to some other common metric. But in terms of global temperature, this is what we convert it to. Watts per square meter, which is our radiative forcing. And so we can have positive or negative radiative forcings. And so in math and science, positive almost never means good. It just means positive in the sense of like a positive number. So positive radiative forcings are changes in the energy balance that cause warming, means energy in is larger than energy out. So you'd get a positive number up here and a positive change in temperature. And negative would be the opposite. So a negative radiative forcing is some change in the energy budget, which is going to cause energy out to be larger than energy in. So you'd get a negative number in the numerator up here. And so a negative change in temperature, a cooling. So I am going to, this is my last thing here, show you all of the radiative forcings that have occurred since the industrial revolution. There's going to be positive ones, there's going to be negative ones. Can you think of, there's going to be natural ones, there's going to be human-caused ones. So before I do that, try to think about what might show up. What are the positive radiative forcings? Have there been negative radiative forcings? What might those be? Have there been natural radiative forcings? And also keep in mind that this has to be a change in the energy budget, like since the Industrial Revolution. That's kind of how we define these things. So it's not, if something is not changing, then it doesn't get included in this. What this is showing is it's like a budget of a company or something where you're kind of adding up, okay, here's all of our sources of income and here's all of our sources of expenditure. And then our bottom line is, whether or not we have profit or deficit. And so what this is showing is all of the emitted compounds, the various things that humans are emitting or the natural changes. And it's just lining everything up and showing, does it have a positive radiative forcing? And that's what's being shown in the bottom here. So positive would be a warming influence. These positive numbers since 1750. And then a negative on the left side of the diagram would be a cooling influence. So I have cooling influence in 1750, warming influence in 1750. And we see here that if you look at each individual component, so we go CO2, methane, here's some other greenhouse gases, halocarbons, nitrous oxide. Here's some gases that end up causing there to be changes in greenhouse gases. Here's something we refer to as aerosols, which are just particles in the atmosphere. But if we look at the size of these bars, we see CO2 is the largest bar and it's positive. And so this is kind of why we talk so much about CO2 in this class, or at least one reason why, is that it is the largest positive radiative forcing since 1750. So it's the largest single contributor to global warming since the Industrial Revolution. And we can see kind of some other stuff on here, like, for example, albedo change due to land use. So that's that other thing I was talking about, where if we cut down forests and put croplands there, which are lighter and which reflect more solar radiation back to space, that should cause a cooling influence. And we can see exactly how big that cooling influence is versus the warming influence from CO2. So our cooling influence is negative 0.15 watts per square meter versus the warming influence from CO2, which is 1.68 watts per square meter. So much smaller cooling influence due to change in land use versus the increase in CO2. And then we also have, look at this, here's this natural change in solar irradiance. That's the amount of incoming energy coming in from the sun. And we have that, oh, it's a warming influence, 0.05, but it's tiny compared to the warming influence from CO2. Oops. tiny compared to the influence due to CO2. And so we see there's other things going on other than CO2. So here's our methane contribution, is this, this orange part of the bar here. And so that's also a major influence on warming the planet. So methane is kind of our second most important greenhouse gas. And then here's the influence from these CFCs that you'll hear about. And then we'll talk more later about aerosols, that basically air pollution from humans also has an influence on temperature, and it tends to have a negative influence on net. So you can kind of imagine, right, that if you have a bunch of air pollution, that's blocking the sun from reaching the surface of the planet. So that's increasing this reflected solar radiation. And so that has a cooling influence. And so that's, from the perspective of temperature, is good from, you know, if you don't want the planet to warm anymore. But of course, it's not good for health reasons. So just putting everything, you know, together, you can see the influence of everything. And if you add all of these up, then you get these bars at the bottom. And so what this bar is saying, this is in 2011, this is saying that since 1750, between the years 1750 and 2011, we have changed the constituents of the atmosphere and the surface such that we are experiencing an energy imbalance, a radiative forcing of 2.29 watts per square meter over that time period. And so that should cause warming of the surface of the planet, which is of course exactly what we observe. This is our big punchline graph. Radiative forcings since 1750. The whole point of bringing up radiative forcings is so that we can look at all of these different contributors to warming since the Industrial Revolution and kind of rank them and say what's their relative influence relative to each other. But I wanted to talk about this concept of radiative forcings in the context of some topics that were brought up in the presidential debate. So let's just watch some of this actually right now.
Climate change.
So would I.
Okay. The forest fires in the West are raging now. They have burned millions of acres. They have displaced hundreds of thousands of people. When state officials there blame the fires on climate change, Mr. President, you said, I don't think the science knows. Over your 4 years, you have pulled the U.S. out of the Paris Climate Accord. You have rolled back a number of Obama environmental records. What do you believe about the science of climate change, and what will you do in the next 4 years to confront it?
I want crystal clean water and air. I want beautiful, clean air. We have now the lowest carbon. If you look at our numbers right now, we are doing phenomenally. But I haven't destroyed our businesses. Our businesses aren't put out of commission. If you look at the Paris Accord, it was a disaster from our standpoint. And people are actually very happy about what's going on because our businesses are doing well. As far as the fires are concerned, you need forest management in addition to everything else. The forest floors are loaded up with trees, dead trees that are years old, and they're like tinder, and leaves and everything else. You drop a cigarette in there, the whole forest burns down. You've got to have forest management.
What do you
You've got to have cuts.
What do you believe about the science of climate change, sir?
I believe that we have to do everything we can to have immaculate air, immaculate water, and do whatever else we can that's good. You know, we're planting 1 billion trees, the Billion Tree Project, and it's very exciting.
Do you believe
for a lot of people.
that human pollution, greenhouse gas emissions contributes to the global warming of this planet?
I think a lot of things do, but I think to an extent, yes. I think to an extent, yes, but...
So he said, I think a lot of things influence temperature, but humans do to some extent. So I want to think about this in terms of our radiative forcing diagram. And so the way that I've kind of rephrased this is based on this diagram, what fraction of global warming, which this is what the diagram shows, contemporary global warming, do you think is caused by increases in greenhouse gas concentrations. So is it like what Donald Trump said to some extent? So is it some, like 30%? Is it half, 50%? Is it most, 75%? Is it all, 100%? Or is it more than all, 130%? So these first 7 rows, the top 7 rows, are essentially our greenhouse gases. So we can assume that the warming contributed from greenhouse gases is these numbers added up. And then you can also go down here and look at what the kind of total warming influence is over that time frame. And so that's around 2.3 watts per meter squared. So then, based on those 2 pieces of information, think about how you would calculate the greenhouse gas contribution to the total warming that we've seen. It's kind of a weird calculation, but I'm doing it for a reason. I mean, it's interesting. But yeah, so this is the answer. The answer is E, more than all, 130%. So this is really important, right? Because you hear this all the time of like, oh, humans contribute to global warming, but it's probably not a big contribution. Or yeah, it's what Trump said. It's to some extent, yes, but he's basically inferring or telling you that some other cause is responsible for most or more than most of the warming. But this is saying, no, it's not only that humans are responsible for 100% of the warming, it's actually more than 100%. And I'll explain why that is. But so here's how the actual math works, is that if you add up all these numbers, these little watts per meter squared here, then you get about 3 watts per meter squared. And if you look at what the total is, it's about 2.3. And so if you want to do the greenhouse gas contribution to the total, you just divide this number, 3 watts per meter squared, divided by the total. And so you get 1.3 or 130%. So you're getting more than the total amount of warming is coming from increases in greenhouse gases. And so how does that work? Like, it doesn't really make sense at first, right? And it's because why? So if you have a bunch of influences on temperature, and some are positive and some are negative, then your total, can be in between, or will be in between. So that's what this is saying, is that you're adding up all of these numbers. You add up these positive numbers and these negative numbers, and you get this at the bottom. But then if you then take the greenhouse gas component, you add those up and you compare it to what the total is, you're going to get more than 100%. And so what that is saying is that if it wasn't for these negatives, so basically the aerosol part that reflects more sunlight back to space, if it wasn't for that, then we would have seen more warming than we've actually seen. So if anything, we have cancellation, so that the warming that we've seen is less than what greenhouse gases alone should have caused or would have caused by themselves. So greenhouse gases, a simple way of saying it is just greenhouse gases are responsible for all of the warming that we've seen. But technically speaking, they're responsible for more than all of the warming that we've seen. And so it's not a situation where you can just say, well, it's part of it. It's to some extent. So Trump is wrong in that claim. So I'll show you this in a different way as well. Sorry. So this is a nice visualization from Bloomberg. So this shows basically simulations of temperature over time where they use climate models to basically, so a climate model is like what you're using with En-ROADS, except it's a different kind of model. It's like a three-dimensional representation of the Earth. But with these climate models, you can kind of stick one radiative forcing in at a time and see what that should have done to temperature. So this shows what we've actually observed in the 20th century, or at least 1880 to 2014. And then it puts on here what the temperature should have done if you just kind of put one radiative forcing in at a time. So again, 1880, 2014, this is what we've actually seen. This is the warming that we've seen, global average temperature. And then this shows, this is not a radiative forcing we've actually talked about, but this shows what should have happened if only the Earth's orbital changes were taken into account. So we see that should not have caused much change. This is what would have happened if only the sun, the change in the sun, was affecting the Earth's climate. So we saw in the radiative forcing diagram that that's just a tiny little positive radiative forcing. So we do expect that we should have seen some warming. So this line is a little bit lower at the beginning and a little bit larger at the end, but it's a very small influence. Volcanoes are not a radiative forcing that we've talked about yet, but we've had some major volcanic eruptions in the 20th century. And when those happen, we would have cooling because it reflects more light back to space. So this is what the temperature should have done if only volcanoes were influencing it. And then this is kind of all of the natural factors together. So the sun, the volcanoes, the Earth's orbit together, this is what the temperature would have done or should have done if only those things were acting on the temperature. And then we can start bringing in human changes. So this is the change in land use. So this is a cooling effect, mostly from deforestation and albedo. Or this is exclusively from the albedo effect. Actually, is cutting down trees, increasing albedo, and so then that's a cooling effect. That's what would have happened if only that was causing temperature change. Here's our aerosol pollution, our cooling effect from aerosol pollution. So more radiation reflected back to space should have caused cooling over this time period if that was the only thing that was going on. And so this is another way of showing that greenhouse gases are more than 100% responsible for the warming that we've seen. Is that if you put together nitrous oxide, methane, and carbon dioxide, our major greenhouse gases, and you put that into a climate model, it says that we should have seen more warming than we've actually seen. And so that means that if you were to do the fraction, if you were to say, okay, it's warmed, 1 point in this diagram, it's like 1.8 Fahrenheit since 1880, and then what fraction of that is being contributed to by greenhouse gases, you'd have a larger number there, and so you get over 100% again, doing kind of the same type of calculation for that. So greenhouse gases are more than 100%, more than totally responsible for the warming that we've seen since the Industrial Revolution.